So for real numbers, we have the following theorem. For every non-zero real number a, it has a multiplicative inverse. The multiplicative inverse of a, that is a inverse, is 1 over a. So the multiplicative inverse of a number has the property, if I multiply a by 1 over a, that's a divided by a, which gives me 1, which is the multiplicative identity. So we can do the same thing for 3. So the multiplicative inverse of 3 is the same as 1/3. And if we take 3 times 1/3, we're going to get the number 1. So the only number that doesn't work for is 0, because 0 does not have a multiplicative inverse. So example 2 asks us to solve a super simple equation. And I know we all know how to solve this, but we're going to solve it in a slightly different way. Most of the time, if we have this equation, 3x equals 12, we would say, okay, well, we need to undo the 3. So we would divide both sides by 3. Well, we can solve this equation by using the multiplicative inverse. And what I mean by that is we found the multiplicative inverse of 3 was 1/3. So I can multiply both sides of the equation by 1/3. 3 times 1/3 we know is 1, so that's 1 times x equals 1/3 times 12 is 12 over 3. Well, 1 is the multiplicative identity, so 1 times anything is just the anything. So we get x equals, and 12/3 reduces to the number 4. And if we solve this the canonical way, by just dividing by 3 on both sides, we'll see that we get exactly the same thing, right? Which is 12/3, which indeed reduces to the number 4. So you might be saying, well, why would we want to solve it via multiplicative inverses as opposed to the traditional way? Well, it turns out that, as I mentioned, subtraction and division don't really exist in mathematics. They were invented to help certain things make more sense with real numbers, but when we start abstracting those things, division and subtraction don't abstract so well. So we run into some issues, as we're going to see. All right, this should take you just a moment, but go ahead and resolve the following equation. 5x equals 125. All right, so to solve this equation, we need to find the multiplicative inverse of 5. So 5 inverse is going to be 1/5. And if we multiply both sides of this equation by 1/5, we get x is equal to 125 over 5, which reduces to 25. All right, in our next example, we want to multiply the two given matrices together. So we have A times A inverse if A is the matrix 3, -17, 1, and -6. And A inverse is 6, -17, 1, and -3. All right, so let's do our multiplication. So we go across the row and down the column. So we have 3 times 6 plus -17 times 1. Across the row down our second column, we have 3 times -17 plus -17 times -3. Now we're going to go across row 2 down column 1. So that's 1 times 6 plus -6 times 1. And then lastly, we go across row 2 down column 2. So 1 times -17 plus negative 6 times negative 3. So we start multiplying and adding. We get 18 minus 17, so that's 1. Here we get negative 51, and a negative times a negative is a positive, so plus 51. So negative 51 plus 51 is 0. And then 1 times 6 plus, well, negative 6 times 1 is negative 6, so that gives us 0. And then we have negative 17, and a negative 6 times a negative 3 is positive 18, so we get 1. So when we multiplied A and A inverse together, so these two matrices, we got this matrix, which is the 2 by 2 identity matrix. So we note that the same thing is happening here as that was happening here. When I multiplied a number by its multiplicative inverse, I got the number 1. The matrix analogy of that is, if I multiply a matrix by its multiplicative inverse, I will get the identity matrix of the same size. Okay. So in the previous example, we talked about what happens if you multiply a matrix by its inverse. We didn't talk about, well, how do you find the inverse of a matrix? So to find the inverse of a matrix, we are going to do the following. The first step that we're going to do, so step 1, is we're going to join the matrix with the identity matrix of the same size. So in this case, we have a 2 by 2 matrix, so we're going to use the 2 by 2 identity matrix. So that's the matrix 1, 0, 0, 1. And when we say join, we're going to create a new matrix that is a 2 by 4 matrix. So we have 3, 1 is our first column, negative 17, negative 6 is our second column. And then we're going to make a 2 by 4 matrix with the identity matrix on the right side. So we make our original matrix here, the identity matrix of the same size on the other side. So we now have an n by 2n matrix. So we had a 2 by 2 matrix, so now we have a 2 by 4 matrix. So then what we're going to need to do, step 2, is get the matrix into reduced row echelon form. We can do that by hand if we wish. I'm going to type it into the calculator. So we have our 2 by 4 matrix. So we go matrix, we go over to edit, 2 by 4. We have 3, negative 17, 1, and 0. And we have 1, negative 6, 6, 0, and 1. So then we go second matrix, go over to math, and we go all the way down to RREF. And then we select our 2 by 4 matrix A. And after we RREF our matrix, we end up with the following. So step 3, if the matrix has 1s on the main diagonal, equivalently, the left 2 by 2 matrix is the identity, then the right 2 by 2 matrix is the inverse. So we'll notice we got the matrix I over here. The matrix on the other side is then A inverse. So in this case, A inverse is equal to 6, negative 17, 1, and negative 3. If the left-hand side is not I, the matrix is not invertible. And is called singular. So if somebody tells you that a matrix is singular, that means it does not have an inverse. We'll see an example of that a little bit later.
Professor?
Yeah. And find the inverse of this matrix. So once again, it's a 2 by 2 matrix. So we're going to join it with the 2 by 2 identity matrix. So 1, 0, 0, 1. And if I were trying to find the inverse, I would have to get, I want to get the identity on this side. And if I can, then whatever's on the other side is going to be the inverse. So I'll do this one by hand. So we have 5 times row 1 plus row 2 to replace row 2. Well, that's going to give me 10, negative 65, 5, and 0, and negative 10, 65, 0, and 1. And if I add those up, I get 0, 0, 5, and 1. So my new matrix would be 2, negative 13, 1, 0, and then I replaced row 2 with 0, 0, 5, 1. So we're going to notice we have a problem. It is impossible to get a 1 in position 2, 2, right? So the matrix is singular and does not have an inverse. So I did one row up by hand to show that, but let's do it on our calculator and see what the end result would look like. So I'm in my 2 by 4 matrix. I would have 2, negative 13, 1, and 0. And then I had negative 10, 65, 0, and 1. So then if I RREF matrix A that I just saved in, well, notice I get that same row of zeros when I do it on my calculator. So once again, we did not get the identity on the left-hand side. So when we look at our comparison, so we get the same thing. The matrix is not invertible. So for real numbers, we had the property that every non-zero real number has an inverse. That is not true for matrices. There are non-zero matrices that don't have inverses. Like example, this one, right? That matrix is not equal to 0, but it does not have an inverse. So it turns out there is a formula for finding the inverse of a 2 by 2 matrix. Turns out this formula generalizes, but it gets really, really ugly for anything bigger than a 2 by 2 matrix. It also gives us a nice check for 2 by 2 matrices. So if we have a matrix A, B, C, D, and AD minus BC is not equal to 0, then 1 over AD minus BC times the matrix D negative B negative CA is the inverse. This part is actually nice to know. It says if A times D minus B times C is 0, then the matrix is singular or not invertible. So if we go up and check that for this matrix, if we compare it to our A, B, C, D, A times D, so 2 times 65 minus negative 10 times negative 13 gives us 2 times 65 is 130. A minus times a minus times a minus is going to be negative, and 10 times 13 is also 130, which gives us 0. So AD minus B times C equals 0. So that matrix was not invertible. So we know immediately that that matrix was not invertible. We're going to find the inverse of that same matrix once again, this time using this theorem. So we identify our A, B, C, and D. So our A is going to be 3. Our B is negative 17. Our C is 1. And our D is negative 6. So we can do AD minus BC is going to be 3 times negative 6 minus 1 times negative 17 and that gives us negative 18 minus minus makes it plus. 1 times 17 is 17. We get negative 1. Okay, so then our inverse is equal to 1 over AD minus BC. So 1 over negative 1 times the matrix D, so negative 6, negative B is going to be a negative 17, and then negative C, our C value is 1, and then A, our A value is going to be 3. So that gives us, in the front, negative 1, then we have negative 6, positive 17, negative 1, and 3. And then we do the scalar multiplication, so we multiply in the negative 1, and we get the matrix 6, negative 17, 1, and negative 3, which we'll note is the same matrix that we got above, right? 6, negative 17, 1, and negative 3. So 6, negative 17, 1, and negative 3. So our formula for A inverse is 1 over AD minus BC times the new matrix D negative B, second row negative C, A. All right, so now we want to use the inverse to solve the matrix equation A times X equals B. Turns out that we can solve this matrix equation in exactly the same way we were solving this, because this is really just A times X equals B. So to solve this equation, what did we do? We used the multiplicative inverse on both sides of the equation. Well, it turns out we can do the same thing with matrices, because we can also form an equation with matrices. So our theorem says if A is a non-singular matrix, then the solution to A times X equals B is X is equal to A inverse B, and the solution is unique. All right, so if A is a non-singular matrix and we have the matrix equation A times X equals B, we can then multiply both sides of the equation by A inverse. Well, when we do that, A inverse times A gives us the matrix I. But I times any matrix just gives you back that matrix because I behaves like 1. So indeed, the solution then is A inverse times B. Furthermore, if the matrix is non-singular, the solution is guaranteed to be unique. Well, suppose Y is also a solution. Then we would have the equation A times Y is equal to B. Well, then I could take my original equation, multiply it by negative 1, and do elimination, add the two things together, and that would give me AY minus AX is equal to B minus B. So that would be the 0 matrix. I could then factor out my A, and that gives me Y minus X is equal to 0. If I multiply both sides of this equation then by A inverse, the A and the A inverse reduce out, and I get Y minus X equals, and A inverse times the 0 matrix behaves like 0 is going to be 0. So then I just have Y minus X equals 0. I add X, and what does that tell me? Oh, y and x really had to be the same thing. So this theorem tells us two things. It says if A is a non-singular matrix, the equation AX equals B has a solution, moreover, what the solution is, which is A inverse B, and that solution is unique. There are no other solutions to that equation. All right, so let's go ahead and solve this using a matrix equation. So to solve using a matrix equation, the first thing we do is we write the system as a matrix equation. So we'll have 3, 1, negative 17, and negative 6 times the column vector xy is equal to the column vector 10, negative 5. So then step 2 is we multiply both sides of the equation by A inverse. So this is A, this is X, and this is B. So we're going to multiply both sides of the equation by A inverse. So that matrix A is the same one that we've used in the last several examples. So we know that the inverse of the matrix A, so 3, negative 17, 1, and 6, is the matrix that we have right here from example 6. So we would have 6, negative 17, 1, and negative 3 times 3, negative 17, negative 17, 1, and negative 6. And we know from example 3, when we multiplied them together, what did we get? I. So this equals I, or the 2 by 2 identity matrix, and that's by example 3. So that gives us this matrix times this is equal to, we go across the row and down the column, so 6 times 10 plus negative 17 times negative 5. And across the row and down the column, so 1 times 10 plus negative 3 times negative 5. But the identity matrix times anything gives us xy. And this gives us 60 plus 17 times 5 is 85. So that gives us 145. And 1 times 10 plus 3 times 5 is 15 gives us 25. So then, using matrix equality, x has to be the same as 145, and y has to be the same as 25. So that gives us x equals 145, and y equals 25. And we then have the solution to that linear system. So we've essentially solved this matrix equation by multiplying both sides by the inverse to isolate the column vector xy, and then once we've done that, we just read off the values from the resulting matrix. All right, so now in the interest of full disclosure, we've been finding the matrix inverse by hand. Turns out we can use a calculator to find the matrix inverse. So we've used this matrix inverse several times. Well, let's go ahead and do it again. So the first thing we need to do is put in our matrix A. So put in our matrix A, we go over to edit. This time it's going to be a 2 by 2 matrix. So we go 3, negative 17, 1, and negative 6. Go back to our home screen. We're going to select our matrix A, and then we're going to hit our inverse key. So that's the x to the negative 1 key. It's the same key we've been pressing to go into the matrix, we just don't press second. And we hit A inverse, and what does our calculator tell us? Oh, that same matrix that we've gotten several different ways by using the formula, using reduced row echelon form, and a few other things. We can also get A inverse by just asking nicely. We can also perform that multiplication in our calculator. So let's go up and take a look at this again. So we had matrix A times this equals B. We've got matrix A in our calculator. Let's go over to edit and put matrix B in. So in this case, matrix B is a 2 by 1. And we put in our two values, so 10 and negative 5. And from our theorem, we know that the solution x is A inverse times B. Well, that's exactly what this was right here. This is A inverse times B. Well, we can do that right in our calculator. So we go second matrix, we grab matrix A, we hit our inverse key, second matrix, and then we choose matrix B, and we press enter, and we get A inverse times B is equal to this. Oh, well that kind of looks familiar actually. This gave us the same values, 145 and 25, that we got essentially doing it all by hand, right? So with matrices, especially anything more than a 2 by 2, so in these examples, I worked all of the problems using 2 by 2 matrices because they're manageable by hand. Once they get much larger than a 2 by 2 matrix, you will want to use technology 100% of the time. So for a 3 by 3, you don't want to do RREF and all that stuff to find the inverse. It is just way too much